July 1st, 2025. Anomalous Interstellar Object 3 Atlas was first cataloged by Wide Field Surveys, and for many days, it resembled a routine discovery, a small, fast visitor on a hyperbolic trajectory. Then the James Webb Space Telescope recorded a concentrated infrared glow centered on the nucleus, steady, 3 times brighter than standard models predicted for an object at that distance. Investigators described the initial data as a single, unresolved thermal source, not a diffuse coma.
Discovered on July 1st by the NASA-funded Atlas survey.
Within hours of that first infrared alert, teams across multiple facilities turned their instruments. Hubble imagery, optical survey archives, and the transiting exoplanet survey satellite were re-examined. TESS images later revealed an earlier detection on May 7, 2025, which shifted the timeline of observation and implied unusually early activity. Observers noted that the object was active well beyond the orbit of Jupiter, where normal cometary sublimation is typically negligible. On August 6, 2025, the JWST NearSpec group, led by Dr. Lena Morovich in this account, published an internal memo describing a repeating thermal pulse. The heat signature rose and fell every 4 hours with striking regularity. By contrast, photometric rotation studies showed a rotation period near 6 hours. The two rhythms did not synchronize, suggesting the thermal source was internal rather than a surface feature, rotating in and out of sunlight. A parallel discovery came from radio observatories. Arrays in North America and South Africa reported a narrowband radio pulse coincident with the infrared rhythm. Fourier analysis returned a carrier signal that recurred every 4 hours with a spectral purity inconsistent with simple cosmic noise. Cross-checks ruled out local interference and known satellite spillover. Independent verification from at least 2 separate hemispheric arrays strengthened confidence that the radio emission originated at the object rather than in the receiving systems. Spectroscopic analysis added further complexity. Teams reported abundant carbon dioxide in the extended cloud, with a CO2 to H2O ratio reported near 8:1, substantially higher than typical solar system comets. High-resolution spectra also showed absorption features that resisted catalog matching. A subset of lines resembled theoretical profiles for engineered materials or uncommon alloys. Another subset hinted at high reflectivity and structured lattice signatures not normally associated with natural dust.
And it was first detected as a speck of light moving relative to background stars.
Observers recorded a sudden flare in mid-August. On August 18, 2025, instruments registered a roughly 40% increase in thermal output in less than an hour. The increase was global in the sense that different telescopes and detectors reported a coincident spike. Orbital solutions updated with post-flare astrometry showed a small but measurable trajectory perturbation. Analysts debated whether the flare could explain the course change via asymmetric outgassing or required localized momentum input beyond standard cometary mechanics.
The biggest question is whether the reflection of sunlight is coming from a solid surface, in which case, as you pointed out, it could be as big as 40 kilometers, twice as big as Manhattan Island.
Consider the rhythm numerically. The thermal pulse repeats every 4 hours, that is, 1 pulse per 4 times 60 equals 240 minutes. If a rotation period is 6 hours, that equals 6 times 60 equals 360 minutes. Comparing the two, 360 minus 240 equals 120 minutes difference between rotation and pulse intervals, a misalignment suggesting independent timing mechanisms. Investigators organized into several working groups. An observational consortium coordinated high-cadence photometry and radar attempts. A spectral analysis panel focused on atomic and molecular line identification. A dynamics team explored orbit propagation under different thrust models. A communications task force attempted controlled transmissions to the object in the form of simple mathematical sequences, prime numbers, basic atomic constants, and the periodic table. A reply, narrow in band and time-locked to the transmitted windows, was reported in internal logs and subjected to immediate verification. Scientific debate shifted rapidly from routine characterization to question framing. 4 principal models were considered and tested systematically: enhanced sublimation of exotic volatiles, buried radiogenic heating, coordinated dust-driven plasma effects, and an engineered or active system. Each model explained some facets, yet failed to account for the whole chain of observations. For instance, sublimation of CO2-rich material can yield extended activity at large heliocentric distance, but does not naturally produce a stable, narrow-band radio carrier linked to a precise thermal rhythm. The dynamics team quantified the flare trajectory correlation. Using post-flare astrometry, they measured a small change in the object's velocity vector. The The reported delta V was small in absolute terms, yet significant relative to the object's mass estimate. If, as one model suggested, the flare produced directed mass loss equivalent to a tiny impulse, that impulse translated into a measurable orbital correction. Observers emphasized the arithmetic. A modest momentum change, when applied over interplanetary distances, can accumulate into a perceptible deflection. Data security and protocol discussions followed. Major agencies invoked contingency procedures, and data feeds shifted to prioritized channels for coordinated analysis. Public announcements were measured and cautious. Agencies released calibrated images and formal uncertainty estimates, avoiding speculative language. At the same time, scientific groups pressed to publish preliminary findings in open venues to invite peer scrutiny. A pivotal observational window approached in late September. The object was predicted to pass relatively near Mars's orbital plane in a narrow interval. Teams prepared coordinated campaigns, space-based infrared monitoring, large aperture optical imaging, and radar mapping where feasible. The central question was whether higher spatial resolution would resolve the nucleus or reveal compact structures within the coma. If structured emissions, collimated plumes, or localized metallic signatures were present, they would provide decisive constraints on formation models. Technical evidence remained nuanced and constrained. Reported periodicity was quantifiable, 4-hour pulses and a 6-hour rotation. Reported brightness exceeded modeled expectations by a factor of 3, that is, measured intensity, say 3 times expected intensity. Spectral line identifications were tentative and catalog incomplete. Teams published line lists with confidence intervals rather than definitive material assignments. Radio signals, narrowband and time coherent, persisted across observing nights with signal-to-noise ratios sufficient for repeated cross-correlation, but not yet for detailed modulation analysis. At the height of the campaign, one observation produced the most dramatic change. A high-cadence instrument captured a sequence in which a thermal pulse, an intense narrowband radio burst, and a localized optical brightening occurred within a tightly linked interval. Multiple independent datasets recorded the coincidence. The timing precision of those events and their cross-spectral coherence challenged the prior assumption of passive behavior. Analysts labeled the event the conjoined pulse, pending further reproducibility checks. Interpreting the conjoined pulse required restraint. Investigators assembled 2 working hypotheses: a complex natural mechanism that coincidentally couples thermal, electromagnetic, and dynamical effects, or an active internal system capable of coordinated energy release and electromagnetic leakage. Both scenarios carried profound implications. A natural process would expand models of interstellar body composition and physics. An active system would represent the first detection of an engineered responsive mechanism beyond Earth. Throughout, the investigation emphasized reproducibility and error control. Teams published raw and calibrated data where permissible, documented calibration sequences, and provided simple arithmetic justifications when recording factors and ratios. For example, intensity multipliers were given as measured values divided by model predictions. Pulse intervals were shown as measured seconds converted to hours by explicit multiplication with 1/3600 as needed. Public reaction varied from skeptical interest to alarm. Scientific institutions maintained a neutral stance, encouraging data-based commentary. Amateur astronomers contributed valuable imagery, particularly during observing windows when professional facilities were constrained. Their contributions augmented the high-fidelity datasets and sometimes provided lead indicators of rapid changes. As the object continued its inbound and outbound passages, the immediate future centered on further high-resolution spectroscopy, continued radio monitoring, and attempts at in-situ investigation if mission design permitted. Engineering consideration for any intercept mission faced technical risk. The object's environment contained ionized gases and particulate signatures potentially hazardous to spacecraft electronics. Agency planners discussed protective shielding, robust communication links, and the feasibility of a rapid response probe under tight launch windows. No single dataset yet suffices to resolve the anomaly. Multiple independent confirmations, repeated under varying conditions and instruments, are necessary before any extraordinary claim can be accepted by the scientific community. This is basic scientific prudence and methodological rigor today. The investigation continues under watchful collaboration, balancing openness and caution. Science advances by confronting anomalies with disciplined measurement and skeptical testing. Whether the recorded pulses, the radio carrier, and the spectral oddities reflect an unfamiliar natural phenomenon or evidence of an engineered system, they demand careful, patient inquiry. Imagine the consequence of each path. If natural, planetary science must expand to encompass materials and processes absent from current catalogs. If engineered, the discovery would force a re-examination of assumptions about distribution and detectability of technological systems. The investigation continues under watchful collaboration, balancing openness and caution. Observatories will keep their instruments trained, analysts will refine models, papers will be written and revised. The mystery recorded in those infrared scans remains unresolved, and that uncertainty is where discovery lives. Remain observant and remain curious.